All right. Okay. All right. So thanks for coming and listening to me. So I'll be talking about radiative transfer and line formation. And because this really sounded like a lecture talk, I went for like a Blackboard style theme, but I'll not be writing on the Blackboard, so don't worry. All right. Radiative transfer, like why is it important? Exoplanets, which is the topic of this workshop, they are studied remotely. It's kind of in the definition, they're not in the solar system. And we have to do that through radiation. So the processes that we can use for that is emitted light by the planet, scattered light by the planet. So for example, light that the planet scatters that has emitted itself, or stellar light that is blocked by the planet when it passes in front of it. And we've already seen this directly imaged planet system here. This is HRI 799E. And if you snap pictures over multiple years, this is what it looks like. And here we can really see the light emitted by the planet. There's another way of measuring emission from a planet. This is for transiting planets. So either they can vanish behind their star, and then we can take a differential measurement between the planet just before it vanishes behind the star and when it's gone, and then we can back out the planetary flux. Or we can measure also the flux modulation as it goes around the planet. We see more of the night side, more of the day side as it goes around. And also it can block the light of its star, which is called transmission spectrum. But we'll not talk about transmission spectra. This is covered by Hannah Wakeford's talk later this week. So we'll only discuss emitted and scattered light here. All right. So to do this, we need to describe the interaction between electromagnetic radiation and the atmosphere. And if we really want to do this, we have to solve Maxwell's equations, which is annoying because they're complicated. However, there's something really useful. It's kind of customary and also allowed even to work in the limit of geometric optics. And this is a really useful assumption that we can make. So geometric optics, this is the definition I got off Wikipedia. This is if the wavelengths of the photons are much smaller than the structures they interact with. Imagine the photon being much smaller than the atmosphere, for example. And it would also mean that the photons are much smaller than like cloud particles they interact with, which is not always the case. But what we can do there is that we can actually do some work ahead of time and solve the Maxwell equations for this process, and then kind of save this as cross sections and still work in the geometric limit approximation. And what holds then is that energy actually, or radiation, just propagates along straight lines, and it makes our life much easier. What we cannot treat this way is refraction. So if the refractive index is changing as a function of distance, light rays would be bent, but that's often not so important anyway, so we can get around this. Right, so a very useful quantity for doing this is the so-called intensity, which is just energy traveling along a ray per unit area, time, frequency, and direction, which is also called per solid angle. And the more mathematically way of writing is I, intensity equals dE, energy, dA, area, dt, time, d nu frequency, and the omega, which is the solid angle or the direction. And you can really imagine it like this. You have a ray of light that's going on a straight line in this direction. And this vector n is the unit vector that points in the direction of travel, and it's kind of pointing into the solid angle elements. They're kind of the same thing. So whenever I talk about integrating over direction, I mean integrating over all solid angles. And yeah, there'll be a bit of math in this talk just because of the title. Sorry. So we just discussed intensity. So what is flux? When I heard about intensity for the first time, I confused it with flux, because flux we encounter a lot of times in astrophysical lectures, even before we had radiative transfer, and I want to spare you this confusion. So intensity is if you just integrate the intensity over all directions passing through a detector. And because it has to pass through the detector, we are only interested in the light that goes through the detector perpendicularly. We're not interested in the light that goes parallel to the detector because it will not enter the detector. So we can imagine this like this. So this is the detector. It's like a rectangle seen from the side, like in 3D, it's kind of projected. This is the normal vector standing on the surface of the detector, delta A, and A has the length of the surface area. this is the intensity shooting through the detector, and there's an angle between the two. And this angle will help us to calculate what's going through the area perpendicularly. And right, so intensity was defined like this, and then flux is just defined like this. So we have integrated out the solid angle dependence. And the actual definition of flux is this. And it's actually quite easy. So we just integrate the intensity, which is a function of direction at a certain location over all directions, so over the solid angle, weighted by the scalar product of the direction of the ray and the normal of the surface area. That kind of makes sense, right? If these are perpendicular, then no energy passes through the detector, and if they are parallel, the light just goes straight through the detector. And then we normalize by the detector area again, because delta A is not a unit vector. So to make it a bit more concrete, we can calculate an example. We can measure the flux by a planet far away. So it looked like this. I drew this. I hope you can read it. So this is the detector area, delta A. The planet's at distance r, which is very far away, and the rp is the planetary radius. And then what we kind of have to know is what is the solid angle subtended on the plane of the sky by the planet. So we can just calculate this opening angle here, theta, which is in the small angle approximation, rp over r, and then the area, which solid angle is kind of the angle area, just pi theta square is pi r planet square over r. So we can just now look at our equation here. So because the planet is so far away, and we usually rotate our telescope to face the planet, n and delta A will be parallel, because if we wouldn't do that, we wouldn't see the planet. So we kind of already can pull out the delta A out of the integral, and it kind of drops away. And we can also assume, just for a second, just for the sake of the argument, that the intensity emitted by the planet into the detector does not depend on the location on the planet, and it's also isotropic. And these are big assumptions, but we can just make them for the sake of the argument for now. And if we do this, we can pull the intensity out of the integral, and we are left with this. Flux equals pi times I, our planet over r square. If I is isotropic, and the same everywhere on the planet, and this is not always necessarily the case, but it's good to learn about this. So this is really what we're all used to, right? Flux depends on distance as 1 over r square. So major results, we learned something new or not. But it holds, and that's important, that the intensity along the travel direction is 0. The density gradient is 0 if in the absence of extinction, emission, and scattering. And this is already the equation of radiative transfer in its most simple form. Intensity is just constant. And that kind of confused me initially. Yeah, shouldn't it change as 1 over r square? So hopefully you'll never suffer from this. Right. Yeah, in the simplest case, intensity is constant. Now let's, make it a bit more complicated. So this is the same form that we just had, expressed somewhat differently. N times nabla I. This is just saying intensity derivative in the direction that the ray is traveling into. So let's add extinction. Right, here it goes. So n times nabla I equals minus alpha tot times I, where alpha tot is the so-called extinction coefficient. And this is just an exponential decay, right? So that's kind of easy to understand. And what is the extinction coefficient? What is the source of extinction? There are two processes that dominate, or that are important actually. So one is absorption. So a photon hits like an interaction partner. This could be a molecule, this could be a cloud particle, and is absorbed, so it's destroyed. It kind of heats up this particle a bit and is maybe re-emitted. The energy is re-emitted at longer wavelengths, for example. That's absorption. And the other process is scattering. In this case, the photon is not destroyed. It just interacts with the partner and just, changes direction, essentially, but the frequency is conserved. And because of this, we can just write the total extinction coefficient as the sum of the absorption and the scattering coefficient. All right, so that we already made our equation of radiative transfer a bit more complicated. So we added extinction. What about emission? So we add a new term, just very abstract and a source term kind of. We call this small j here, and this is so-called emissivity. And I mean, what is it, right? It's kind of abstract. Can we kind of gain some intuition about what j kind of is? And then we can make a useful thought experiment. Well, imagine you have light coming off a black body, And light coming off a black body is, the intensity is just equal to the Planck function. So I measured above the black body is B, where this is the Planck function as a function of temperature. And now imagine the light passes now through a medium, a gas, for example, that is in local thermal equilibrium. That means it's characterized by one quantity, that's the temperature, that determines how the energy states are occupied in molecules and atoms, for example. And if there's no scattering, because and if the temperature of the medium is the same as the black body, we don't expect this intensity to change. It should stay constant, because everything is in equilibrium at the same temperature. In this case, we then can just write n times nabla I is 0, and we can solve this for j. And in this case, we find, so n I is constant, n times nabla I is 0, j equals alpha ups times b. And this is very important. This is Kirchhoff's law, or Kirchhoff's law, how we'd say in German. So in local thermal equilibrium, any medium, the emissivity will be alpha ups times the Planck function. Very important to remember. All right, last thing that we'll add, this is the scattering. So we add a third term now to the right-hand side of the equation. And this is the scattering term. And maybe it looks kind of complicated. Well, I don't know, maybe a bit as an integral, but it's actually quite easy to understand. So we have a ray that travels in direction n. Let's say like here, this is my arm, traveling in direction n. And then we basically ask ourselves, if we have a ray coming in from a different direction, like n prime, what's the likelihood of this ray being scattered into the traveling direction? So like acting and going parallel to my first arm. And this likelihood is expressed by the so-called scattering source function here. And there's just some proportionality factor here, which is the scattering cross-section. Oh, extinction. Oh. Does it work now? No? Test. Is it better? No? Yes, like this? Test. But yeah, I can see it here. Is it very annoying? Okay. Test. Better? Okay. Is that fine? All right. So we were here. So, okay, so this is the scattering source term, and there's this function p, which is the scattering phase function, and this just answers the question, coming from direction n prime, how likely is it to be scattered into direction n? And p is a property of the scattering partner of the photon, so molecule or particle. And we can, again, look at it at an interesting limit. So in the case of isotropic scattering, p is just 1/4 pi. It just has to be normalized because it's a probability density. And then we can actually write n times nabla I equals minus alpha tot I, extinction, plus j, plus alpha scat times j. And j is just the mean intensity, which is also kind of intuitive. You just average the intensity over all solid angles. Right. This actually is what makes radiative transfer so hard. So if you look at this equation up here, you want to integrate this to solve for I. But if you want to do this, you also already have to know intensity at a certain location coming in from all the other directions. And in order to solve for the intensity coming in from all the other directions, you have to have integrated them as well up to this point. So you kind of have to know the solution before you begin. It's kind of like a chicken or egg problem. And depending on the problem, can be hard or easy to solve, but usually in the full beauty, it's done iteratively on the computer, where you start with like a scattering term that's 0, and then you calculate one radiative transfer step, then you update your scattering source function and do this until the problem converges. And the problem there can be that you have like false convergence, or it's just really slow, and there are many techniques to make this faster, but this is what makes radiative transfer hard. All right, so let's look at now we have everything, so it'll become easier from this point. So let's look at the equation in full beauty. So it'll become harder one more time, but then it'll become easier. Because we dropped a lot of implicit dependencies, I just want to show them here once, and then you can forget about them again. So this is showing all the dependencies that there are, like intensity, for example, depends, of course, on location. It depends also on the frequency of the radiation. And as you can see, this holds for this for the total extinction coefficient, for the scattering coefficient, for the emissivity, also the scattering phase function. Everything depends on the location and frequency, because the material properties also depend on location and frequency. Right. Well, to make things more digestible, we drop these dependencies again, but only notation. We have them in mind. And now we make things easier. Let's remove this n times nabla term again. And now we will change to a coordinate system that's parallel to the ray that we're studying, and just express distance as the distance traveled along the ray. And then it looks like this, and this is already much nicer. So di ds, no nabla anymore. And we make it even more simple now. We will change from s, distance, to units of optical depth. Okay, so for this, what's important to know is that the extinction coefficient basically is the inverse mean free path. Okay, I mean, I could shout, but then people online don't hear it, right? No. Is better? No? Okay, I'll try. Sorry, I'm sorry. Okay, so the extinction coefficient is just the inverse mean free path. And we want to go to the so-called quantity of optical depth, which is distance in units of mean free path. So what is a mean free path again? So imagine you have a photon traveling over a length lambda, and well, there's a cross section of interacting with particles in the medium. So if the photon travels at distance lambda, it will kind of carve out this volume here, sigma times lambda, and then these dots here are the particles that it can interact with. And the mean free path is basically, if you multiply sigma, the cross section, times lambda, you get a volume times the number density of particles, and you want this to be 1. So you just want to interact one time on average, like once. So it's the mean free path. And usually we actually work in somewhat different units. So we express cross section per unit mass, kappa. This is called the opacity. And then we don't multiply by number density anymore. We just multiply by mass density. But this is how it's defined. And therefore, alpha tot just lambda to the power of -1 equals kappa times rho. And now we can finally go to optical depth, which is just the distance in units of mean free paths. So delta tau equals alpha tot times ds. So we'll now change from ds to d tau. So we have to divide everything by alpha tot as well. So we have this, and now we divide the whole equation by alpha tot. ds becomes d tau. We get j over alpha tot here, alpha scat over alpha tot here. And then we also lump j over alpha tot and alpha scat over alpha tot in this integral together into a so-called source function. And if we do this, this is the definition of the source function, like I just said. This is the equation that we are solving. And let's put like 3 boxes around this, because this is really what we are solving on the computer, and also what we are solving, thank you, when we are talking about, when we are thinking about solving in our heads, intuitive, like thinking about the problem. I always think about this equation because it's very easy to kind of understand and work with. All right, so, and what's also really cool, if you look at the source function in LTE, and in the case of isotropic scattering, then we just get that S equals epsilon times B plus omega times J. And epsilon is the photon destruction probability. It's just the ratio between the absorption and the total extinction coefficient. And omega is the so-called single scattering albedo, which is basically the ratio between the scattering coefficient and the total extinction coefficient, which is just 1 minus epsilon. So it's kind of, I find this very intuitive, like simple to understand equation, and the source function is just the likelihood of absorption times B in LTE plus the likelihood of scattering plus J in the isotropic limit. Yeah, so this is kind of, I find the most useful form. Okay, now an exercise for you to solve later. I'll show you the solution here. So imagine we have a box of thickness delta tau. Imagine, remember we went from distance s to tau, and you have intensity coming into the box with I0. There's a source function which is constant, and we want to know what's the intensity coming out of the box. And then, I guess you've also seen this before, but just to remind ourselves, this is a solution. Here, basically, I of delta tau is I0 e to the minus delta tau plus 1 minus s e to the minus delta tau. And why is this so useful? Let's look at the limits of the solution. If delta tau is 0, I of delta tau is just I0. Makes sense, right? The box has 0 length, nothing happens. And if delta tau is infinity, goes to infinity, then the intensity just goes to the source function s. Like it's not building up infinitely, it just goes to the source function. And that's a very important result for understanding how lines form in a second. So what that also means, in LTE, all intensities of rays passing through an optically thick medium, optically thick means large delta tau, that is non-scattering, has a temperature T, the intensity that's coming out will have B of T. And that's kind of useful for understanding how lines form as well. All right, line formation. So we'll now go back and talk about one dependency that we have dropped, which is now becoming important again, which is the dependency on frequency. Like the opacity or the cross-section per unit mass depends on frequency. And if you plot this, it looks like this. Kappa, like remember this is cross-section per unit mass. Depends on frequency. In this case, we have like a peak here, which we call a line. Yeah, okay. And if we want to solve the rate transfer equation for such a state, all we do is we use our equation that converts to delta tau again. If you have a box of certain size, delta tau equals kappa rho delta s. And then we just use the exact same solution that we had before for I of delta tau, but we just use the fact that delta tau is changing as a function of frequency if you have a box of a fixed physical size delta s. So this is our delta tau curve. And now when we're solving this, we now are solving again, because now we're interested in physical units again, delta S, maybe the top of the atmosphere, for example, what's coming out of the top. And let's assume also that source function is constant, is equal to B. So this is what we're solving now. Before we had this, right? So we use the exact same equation, but now it's just delta T depends on delta S and nu. But I mean, otherwise it's the exact same thing. So let's make a line. So this is what we had, solution, and delta tau is a function of frequency. So we can have two cases for light going through this box that we just discussed. If the source function in the box is equal to B, and that's smaller than the incoming intensity, I0, what will happen is that in the line wings, there's 0 opacity, delta tau is 0. So the intensity will not change, it will just be I0. But in the peak of the line, delta tau is large, so the intensity will go to B. So you get, and because B is lower than I0, you get like this shape here, which is called an absorption line. There it is. And if B equals B of T and I0 roughly corresponds to a different temperature, B of T0, for example, absorption lines form if T is smaller than T0. And the opposite happens if B is larger than I0, then it stays again out of the line core, it stays at I0, but it goes to a B in the line core and it's larger than I0. This is a so-called emission line, which forms if T is larger than T0. Right, and like I said, or we alluded to, the sign of the temperature gradient in general, like if you have a system that you solve the radiation transfer through, like an atmosphere, the sign of the temperature gradient dTds determines whether absorption or emission lines form. If the temperature goes down in the atmosphere and you look at the flux coming out as you go up, then there will be absorption lines. Okay, so why do we have lines in the first place? Well, they're formed due to quantum mechanics. So as we all remember, energy states, the molecules, atoms, ions, and so on, they are quantized. There are only discrete values that are allowed. And if the molecule changes from one state to the next, one energy to the next, there's an energy difference, and energy can be expressed as h times nu, Planck constant times nu. So if the photon has exactly this frequency nu, it can excite this transition. And these transitions are just state changes in the electronic, vibrational, or rotational state of an absorber. And just to give you one example for water, what are these vibrational modes? Like water can bend, it can stretch symmetrically, it can stretch asymmetrically, and kind of the frequency that the molecules is doing this with kind of determines how much energy is in the system. Right, and if you have seen this before, this is just for reference, you would calculate the line strength using the Einstein coefficients, but if you haven't seen that before, ignore it. Right, so our lines broadened. Imagine this case again. We want to excite a transition, and this transition has one exact frequency. So if you plot the opacity as a function of frequency, that would mean there's just a delta function, basically, where the photon can be absorbed exactly at the energy delta E, and the frequency would be delta E over H. And the question is, do we really have a delta function? The answer is no. So lines are not infinitely narrow, they are broadened. And two effects dominate. Oh, sorry, I can press this button as well. So two effects dominate. One is lifetime-related broadening. So these excited states can have a finite lifetime, and you think about Heisenberg's uncertainty relation, this also means like an energy uncertainty. And there's also Doppler broadening. So the molecules, atoms, cloud particles, they're moving. And if a molecule is moving towards the photon, it will see a higher frequency than the intrinsic frequency of the photon, and can also absorb photons at a somewhat lower energy. And this is called Doppler broadening. Right, and there are two kinds of lifetime-related broadening. One is natural broadening, where excited states decay spontaneously. This is due to quantum vacuum fluctuations. And there can also be pressure broadening, where you are collisionally de-exciting an excited state. And what's interesting there is that the pressure broadening strength is just proportional to pressure. There's also temperature dependence, but the pressure is most important. For the Doppler broadening, if you are in LTE, so then the velocities of the gas and molecules just follows the Maxwell-Boltzmann distribution, and the broadening is proportional to square root of T over M, where M is the absorber mass. So let's look at some examples of how this actually looks like. We now plot log kappa here because it's easier to see the wings. If you don't do that, you just see a line. Looks like a delta function. And let's turn on natural broadening. I still kept the line, of course, in the middle. Normally you wouldn't have that anymore. And you see there's like some wings that give you some absorption outside of the line core. If you add pressure broadening, the whole thing, the wings move up because they have stronger broadening. The core moves somewhat down because you want to conserve the integral. And if you go to even higher pressures, the wings become even stronger and the core goes down even more. If you go to infinitely high pressures, you just get a flat line out. So you kind of smooth out your lines. That's pressure broadening. And there's also thermal broadening. And this, in log y-axis looks like this, like a bell curve, basically, in log units. And if you go to a stronger thermal broadening, it becomes wider and the core goes down again. Right, and to be complete, these are the line shapes for lifetime broadened, the so-called Lorentz profile, where the wing strength is kind of proportional to the 1 over the distance from the line core squared in units of frequency. And for Doppler broadening, if it's Maxwell-Boltzmann, you just get this exponential minus distance from the line core squared dependence. This is just because of the velocity distribution of the particles in LTE. All right, to be complete, of course, these processes are happening at the same time. They're both happening. And usually the line core is Doppler dominated and the line wing is Lorentz dominated. So the effective profile looks like this. This is also known as a Voigt profile. How do you get this? Unfortunately, there's no nice analytical form of this. You have to do a convolution, which is usually done numerically. There are some estimation functions for this if you want to calculate opacities. But yeah, usually you have to do this here to get the full profile. And it kind of makes sense. Like if you are at a frequency nu, and you want to know how likely am I to see the Lorentz wing of a line that sits at, how likely am I to see the Lorentz wing at a frequency nu prime? Then just have to know the likelihood of shifting via Doppler shifts my frequency nu prime into nu. So it's kind of makes sense why it's a convolution. All right, that's almost it. I think, yeah, this is the theory about radiative transfer in its kind of most simple, useful form and how lines form. I want to expose you a bit to the real world, though, by showing you a theoretical model. So actual data is actually often not at high enough resolution to resolve the lines. Thank you. So this here is a model calculation from a review paper by Jane Birkby. And she shows here the flux of the planet as a function of wavelength. And you see the same model at different resolutions here. And this is the color code here, 100,000. So resolution is defined as lambda over delta lambda, where delta lambda is kind of the distance between detector pixels. And then, lambda is the wavelength you're looking at, delta lambda is the distance of detector pixels, actually resolving element, but let's not talk about that for now. And at arc is 100,000, you usually can see individual lines. But for many of the spectrographs we're using, the resolution is lower. James Webb, for example, the high resolution modes have like 2700. So it's like even below the cyan line here. And HST is like 30 or so. So you just get these white boxes here. So why do we make all this effort of doing this correctly, treating the lines with line chords, line wings, and whatnot? The reason is that they're still determining the overall shape that we're seeing in the spectrum. Of course, the lower the resolution, the less sensitive we are to such effects. If you go to infinitely low resolution, again, we just get a flux measurement. But it's still important to take this correctly into account. But of course, it's also true that, that's what I just said, but of course, it's also true that as you go to lower resolution, you lose information. That's just part of the process. All right, so that's it. To summarize, in the absence of absorption, emission, and scattering, the intensity I is constant, and that's the most important quantity of radiative transfer for calculating spectra. This is a useful form of the equation of radiative transfer. It's just di d tau equals minus I plus s, so exponential decay plus the source function. And this is a useful solution. I think if you know all this, you basically understand, except for scattering, which can make things more complicated, but that's basically enough to understand already a lot. So I of delta tau equals I0 e to the minus delta tau, 1 minus s e to the minus delta tau. And absorption lines form in the spectrum if dT/dr, the temperature gradient, is smaller than 0, which is the case often for atmospheres. And emission lines form if the planetary in the planetary spectrum if dT/dr is larger than 0. And r, again, is just the radial coordinate of the atmosphere pointing upwards. And I also, again, want to make this clear. We're talking about emitted flux here, not transmission spectra. This will be talked about later, because emission spectra, they're kind of blocking, transmission spectra, they're blocking the stellar light. So independent of the temperature gradient of the atmosphere, we'll also see absorption, always see absorption lines. Just because the star is so much hotter, we can neglect the emission of light at optical or like stellar wavelengths. All right. Right, lines are caused from the quantization of energy states in molecules, atoms, and ions, and they are broadened, and pressure broadening and thermal broadening dominate. Thank you very much.
Thank you, Paul. And Paul deserves extra kudos for finishing on time despite the technical difficulties. So, which the staff here are dealing with just fine, and we're rolling with. All right, so are there questions in the room first? Started online last time. Oh yes, please ask your question, and then we'll ask Paul to repeat it.
I repeat it. Yes. I'll repeat it. Yeah, this is okay. So the question was, so if we take an actual observation, there are like many lines of different species, for example. Yes, there are many lines of different species, for example. I guess there's also noise. So how certain are you when you have like a model that what you think you're seeing is actually what you're seeing? And this is a very good question. And that's basically what retrievals are all about, that you'll learn about later this week and also do a hands-on session on. You want to do a good job in modeling by including all the molecules that you can kind of think of and include them all in your model at the same time, and then kind of test for their presence via some statistical tools that are there. And you also, of course, have to know your error bars really well to understand whether if you see something, is this true or is it just noise that you're seeing? But in principle, if you kind of leave out an important species that's doing something in your spectrum that you didn't have in mind and you never include it in your models because you don't understand the problem well enough, there's the danger that you just drive something wrong. So we have to be very careful of including what we think are the most important quantities, and also testing statistically. Does it make sense to make the model more complicated, include one more molecule? And also, of course, like I said, if your signal to noise is low, then yeah, it's hard to say things. So you need good models and good signal to noise data.
Okay, questions online?
Yeah, I have some here. Hopefully you can hear me here. So are there any codes that simulate exoplanetary spectra, accounting for multiple scattering of clouds and hazes in a robust way?
Yes, there are. Mine, for example, that you'll use later this week, but there are also other codes out there. Picasso, for example, can do that. Mike Lyne's Chimera code can do that. So they all treat multiple scattering events. You just have to either iterate or use like matrix inversion equations, depending on the limit that you're working in. I think it becomes complicated if you have cloud particles that can have complicated phase functions for scattering. Some codes like mine assume isotropic scattering and then use like a so-called scattering anisotropy factor to speed things up. But I think multiple scattering is something that's regularly included now, and also if you compare the results of different codes, also for the predicted temperature structures, they tend to agree. So I think many of these tools that are out there are good.
Okay, oh, Mike, all for that.
Yes, so scattering complicates. Oh yeah, sorry, of course. So the question by Mike was like, we basically, like, I mean, the equations that are derived included scattering, but all the examples that I showed kind of neglected scattering then. So what happens if we do include the scattering? And scattering can make things more complicated. For example, these limits that I showed, you get like an absorption line for the temperature gradient being negative, and you get an emission line if it's positive, and by extension, if the atmosphere is isothermal, you don't see any lines. But if you're like a strongly scattering atmosphere, you can actually get lines, like looks like emission lines, I think, from a isothermal atmosphere. So there are many also unintuitive. I've not understood this to this day. I followed the derivation in one of your papers, I think, which I could understand, but intuitively it doesn't make, I don't understand it so well, but this can happen, right? So scattering makes things more complicated and can be unintuitive sometimes. And that's good to keep in mind.
Yeah, there's a question here. It's hopefully relatively simple. If two components, for example, H2 and O2, have the same number, density, temperature, and pressure, would their absorption line look the same?
So they, well, not exactly. So first of all, H2 and O2, unfortunately, well, H2 at least doesn't have very strong lines. O2 has a few lines towards the optical. But in general, if you have two species that have lines, the line shape will not always be the same, even if the same pressure and temperature, because the pressure broadening depends on the species itself and also the partner that it interacts with. For example, water self-broadening is much stronger than other molecules that broaden themselves. And the temperature broadening will be slightly different because there's this mass dependency. A more massive absorber will be less broadened, for example, thermally. And also, maybe that leads a bit too far, but if you see one single isolated line, and normally they have pressure broadening and Lorentz profile, but this doesn't go out to infinity away from the line core. You don't always have a Lorentz line wing. It can look different, will decay, and this also depends on the material, like the absorber properties and the interaction partner.
Out where most of the contribution within an atmosphere is coming from?
That's a good question. So the question was, how can we figure out having a spectrum where most of the contribution that we see in the spectrum is coming from? So what you could do, well, by eye it's kind of hard, but if you imagine, look at the lines at high resolution, if it's quite strongly broadened, you will see like the wings are wider. So from the line shape, essentially, you could extract the pressure where it's forming. And from the line shape also, you can extract maybe the temperature, because there's also the thermal broadening that plays a role. And also the relative strengths between different lines, they depend on the level populations in the molecule and the atom. That also helps you to constrain the temperature. And all of this together, seeing the spectral shape in these processes like level population, line shape, help you to constrain the so-called pressure temperature structure in the atmosphere. And of course, you're not sensitive everywhere in the atmosphere. It depends on the optical depth. At really low pressures, the optical depth is just too low. You will not be able to constrain anything. And if it's too deep down the atmosphere, it's hidden by everything that's above, basically.
Okay, so is it possible to add the planet's contribution to the spectrum via the radiative transfer formula like extinctions? Not 100% sure.
I'm also not sure.
Yeah, okay.
I please ask this question on Slack and I'll try to answer it.
Well, given that you're pretty much at the end of this, yeah, could you please address that on Slack?
Yes.
Let's give Paul